Hello, sir. You are on mute, sir. Sir, sir. You got muted. Sir, you are on mute. We can't hear you.
Hello. Yes, so we can start. And this is where we left last time. I hope you can hear me. So we were getting into some of the templates of optimization problems. There are various types of optimization problem, and we are continuing towards that. And last time we saw convex optimization problem, and in particular we saw how we can eliminate equality constraints. Okay, and
Okay.
so there is a way to eliminate equality constraints by knowing the null space information, or in other words, to be more precise, by knowing the general solution of this. Okay, a general solution of this can be given by this. Okay, where x naught is some particular solution and f is the basis of the null space of A. Okay, so all this can be combined as Ax equals to B form here. Yeah, so there is a linear algebra approach where we can eliminate the so we can eliminate the equality constraints. Okay, so these equality constraints can be removed, and we are only left with inequality constraints here. Okay, so if I have a solver where a very good solver with inequality constraints, then okay, I will use that. Okay, and then I will eliminate the equality constraints. Okay, so some specific solver for inequality I can use, but I have to do some change of variable, like in this case I have done. Okay, so this is something we did in the last class. Okay, so moving on, there is something called linear optimization problem. So linear optimization problem looks like the following. So when the objective, okay, so this is objective here. We remember in our notation it's f naught x, and then the constraint functions which are like fix, and other constraint is the equality constraint, which are in our notation it's denoted by hix. Okay, where I is here in this case is like greater than equal to 1. 0 is preserved for the objective, and here I is greater than equal to 1. Okay, there is no 0 here, I guess. Okay, so when the objective function, constraint functions are all affine, okay, then the problem is called a linear program or linear optimization problem. Okay, so sometimes program is used in an analogous way to saying that it's an optimization problem. There is a story that goes that there was a guy who was working on optimization problem, but then in the lab that he was working in, it was more like an applied computer science department. So they didn't like him doing a lot of maths. So like he was using the word programming. Okay, and then those guys were happy that okay, the guy is doing some kind of programming and not really doing too much maths. Okay, so so there is a history behind using the word programming instead of saying the linear program, instead of saying it's a problem, optimization problem. Okay, so that sounds more like a maths problem, right? Okay, so linear program in the general form, it looks like this. So we have checked that the objective function is affine This is of the form gx, so this is affine. Okay, so this is the inequality constraint function, and the equality constraint function is also affine. Okay, so all this is checked. Okay, objective is also. So then we will classify this as a linear program. Okay, you can bring this h on the left and so on, put this in standard form also, it doesn't matter. So these are the processing you may have to do. But if this is of this form, then we will classify those optimization problem as linear optimization problem or linear programming. Okay. Okay. So so if you yeah, so linear, the feasible set in those cases will be some kind of a polygon in some sense, because these are like intersection of like some half spaces and like the planes, okay, hyperplanes. So it could end up as some looking like this, which this set was nothing but the polygon that we defined, or polyhedra that we defined. Okay, so linear programming problems, the feasible sets look something like this. Okay, so it is common to omit d in the objective, because maximizing or minimizing with the presence of a constant doesn't really change the place where I will get the maxima or minima, right? So maximizing or minimizing x square plus 2 is the same place where I will also get the maxima or minima of x square. So this translation doesn't really affect. Okay, so it does not affect affect the optimal. It does affect the optimal value, but does not affect the optimal point. Okay, so optimal point, by optimal point we mean the x star. Okay, so these things can be dropped. Okay, so can be dropped. Okay, so and also maximize as usual can be done by doing a negative of the objective of the minimize. Okay, so this is something we know all along. And so that was linear optimization problem. That's the form of linear optimization problem. Objective affine, inequality constraint affine, equality constraint affine. Now let us move to quadratic optimization problem or quadratic programming, and then there is also a variant of this. It's called quadratically constrained quadratic program. Okay, so let us see one by one. So this is the so-called quadratic program or quadratic optimization problem. So naturally, you see a general form of a quadratic function is of this form, right? General form of a quadratic function, right? We have seen this quadratic function before. So it's sometimes called quadratic function or quadratic form, or form function or a form, right? So any quadratic function can be written in this compact form. Okay, so the second degree terms you can plug in here, first degree terms and the constant terms can go here. This is like just to adjust. Okay, so this scalar you can think of is just a way to adjust so that the gradient looks clean. Okay, because these are like square terms. So if I take a derivative, then I will have a 2 factor there after taking the derivative. So to cancel the 2, I also already like scale it further, because multiplication by half really doesn't change the maxima or minima of it. So constant doesn't really change. If it's a positive constant, then the constant doesn't change the optimal value, optimal point of either of these. Okay, so sometimes you will see some scaling is being done so that the form is like simple and so on. Okay, so what is the nature here? So we can already see that f naught is quadratic. Okay, so that's the first point. Second observation is that the inequality constraint is affine. Okay, so inequality constraint function is affine. Okay, and the third one is equality constraint is also affine. Okay, so equality constraint function is affine, right? So these are the observations we have, right, for a quadratic quadratic program. Okay, and furthermore, some of the things that we are also asking for is this. So it's like positive semi-definite. Okay. Remember, there was an example where we did in the class that if you drop this restriction, then yeah, so it may like it may not. I mean, it may not remain. The objective will not remain convex. Okay. So in a standard quadratic program, like we are maintaining that P is symmetric, semi-positive definite. Okay, so that's additional restriction. S stands for symmetric and plus for semi-definite. And G is a matrix, obviously, M by N, and A is a matrix, P by N. Okay. Okay. So these are the things you have to remember. It has to be exactly in this form. Okay. You cannot put any nonlinear inequality, a constraint function, and so on. Although I have not written explicitly here, from here you should immediately see this as a strict restriction. If general inequality constraints were to be assumed, I would have written general form. Okay. So this is the form of the quadratic program. Now quadratically constrained. So here it was affine constraint, inequality constraint. Inequality constraint, and if I drop this restriction and make it quadratic, let us say step by step. So let us say, rather than saying any nonlinear, let us say we extend it by one step. Let us say going from affine, the next step after affine is like quadratic, right? So this is like quadratic constraint. Okay, so this is quadratic constraint. Other things remain the same. So this is still the affine constraint, and this is still the quadratic. So this is called quadratic constraint quadratic program. Okay, so this is the template of quadratic constraint quadratic program. P still remains, in fact, P and also the Pi. So all P, P0, Pi, all this is symmetric and semi-positive definite. So what we observe is then QC, QP. Okay, so when you read papers, then sometimes people just write QP because it's so standard. So they will just write QP, and for linear programming they will write LP. Okay, so a QC, QP. Okay, so QC, QP. So what do we observe? We observe that we minimize over a region that is intersection of ellipsoids. Okay, when Pi is greater than 0. So one thing we observed, this is something we did in previous classes, is like, so we have looked into functions of this form, and we have seen that if Pi is greater than 0, then it forms like an ellipse, right? So it forms like this ellipse, right? So yeah, so it is like an ellipse, and if you don't guarantee something like this, then you may end up as so these are like ellipsoids, right? And since P is like positive definite, so this means positive definite. Okay, so this also means that the P matrix we have is has eigenvalues positive, right? So what the simplest one I can choose is like, let us say 1 and 2. Okay, I mean simpler one. So which is the diagonal K, and eigenvalues are guaranteed to be positive, and then so these are proportional to major and minor axis and so on, and this will define an ellipse. But the moment I change this P to non-positive definite, so let us say this case, so one eigenvalue I made it negative, one is still positive. Okay, the eigenvalue diagonal matrix is on the diagonal, so this will no longer maintain ellipsoid nature. Okay, so this will be like hyperboloid or something like this, x square minus y square. Okay, so this will maintain like hyperboloid. Okay, so in this case it will be like square root of 2, something like that. Okay, you can write it in this form. Okay, so this will no longer be ellipsoid, this will be like hyperboloid. Okay, so in quadratic program, quadratic QC/QP, we don't allow hyperboloid constraints. We are still maintaining that these Pi are greater than 0. This means that this will remain ellipsoid. So these are nothing but intersection of, because there are multiple of these constraints. So they are like ellipsoids, right? So there are many ellipsoids, and you have to satisfy them simultaneously. This means that these are intersection of these M ellipsoids. Okay. Okay, so that's the QC/QP. Let us move on. Now, in case you can get a special cases of the problem by if you encounter, let us say, pi is equal to 0. Okay, so if it happens that pi is 0, let us say for all I. Okay, say for all I equal to 0, 1, 2, and so on. So if pi is 0, then this means that this guy will be 0, and then this guy will be 0. So this would mean that I will be left with this, and I will be left with this. So in other words, this will mean that this is like a affine. Okay, affine if p0 is 0, and these are also affine if pi are 0 for all I equal to 1 to m. So this will boil down to LP. Okay, in that case. Okay, so linear programs are a special case of a QCQP when pi is 0. Okay, so or it's also a special case of quadratic, obviously. In this case, just this p is 0, and then it falls back to LP. Okay, so naturally a solver that is if your problem is LP, then like this, then you should use a specialized solver for LP. Okay, you should not use a solver that is meant for this. You will unnecessarily do a lot of computation. Okay, so that's why it's important to identify which type of problem you are solving. Now, naturally, we can keep extending. So we can call something called second order cone programming, okay, or second order cone optimization problem. So here, again, the geometry that we learned, all this is now helping us to clearly like propose these optimization problems. So now we know the concept of a cone, and that can be used now, right? Okay, so if you recall from previous classes, then this defines a cone. Okay, so and then it's like intersection of many of these cones. Okay, and this remains affine. Okay, so remember this templates has to be very precise. Okay, so this is called SOCP. You cannot put something nonlinear, although you maintain that the inequality constraint a cone. No, okay, so they are given specific names for exactly this template. Okay, you are not allowed to change affine to nonlinear and still call it cone programming. Okay, that's not allowed. Okay, so it has to be exactly this form. So it has to be of the cone form like this, and it has to be affine objective, and it has to have affine equality constraint. Okay. Otherwise, other things are quite general. So X is like in Rn. AI has no such restriction. AI could be any Ni by N matrix, and F also doesn't have any restriction in the sense of positive definiteness or anything. So other things are general. So the constraint here is a cone, and that's why it's called a cone program. So we call the constraints of the form a second order cone constraint. Okay, so we call this a second order cone constraint, and yeah, again, like if we put Ci to be 0 for all I, then SOCP will be equivalent to QCQP. And if AI is equal to 0 for all I equal 1 to m, AI is equal to 0 for all I equal to 1 to m. Yeah, so AI is equal to 0 for all I to 1 to m. This will SOCP will reduce to LP. Okay, so if this is less than 0, again, this is affine. Okay, so there are various scenarios where so SOCP again, it's like, so it reduces to like QCQP, right? If CI is 0, right? And so because this constraint, because this is a norm, right? So it could be written as this transpose times this, right? So then it will behave like QCQP, because these things are like some X transpose X form. Okay, so it's just that one has to do a little bit more here, because what I have to do is like X square root of P, right? And then So this vector, if I take a transpose square root of px, okay, so transpose of this with square root of px, right? So this is nothing but norm of square root of px, right? So these guys are like, if I'm saying constraint with respect to the norm, it's the same thing as like I'm saying saying a constraint on this, okay? And this guy is indeed x transpose px, okay? So that's how the definition with respect to the norm is actually similar to writing in this form, which is the quadratic form in this case. Okay, so SOCP will reduce to this QCQP if CIs are 0, and similarly AI, if AI is 0 for all I equal to 1 to m, then furthermore, yeah, if AI is 0 for all, not furthermore, but just just AI being 0 is enough, because objective is linear. This becomes affine because AI is 0. It's just a constant norm of B, which is a constant. Okay, and this is affine again. So this remains again linear. Okay. So second order is the most general. So now if we see SOCP is QCQP is QP is LP. Okay. So this is the general trend that we are looking at. Okay. So, and then there are some specific cases in the stochastic regime where you are working with random variables and not necessarily deterministic variables. Okay, So by that I mean this is still LP, but now I'm talking about robust. I mean, it's called robust. There is some name given to this, but what is to be noted here is that now the vectors that you have are like some kind of stochastic vector. In other words, like these are like this could be like random variable. Okay, so I mean there is some uncertainty in these cases. Okay, so I cannot say like I mean, I cannot say like this is like some fixed value, but I can talk about in terms of probability. Okay, so probability that it takes this value and so on. Okay, so these are like there is uncertainty in this. Okay, or in other words, there is a probability that this will take this value in certain form. Okay, so if you happen to work in this those kind of models, then you will put this in this framework. If you know that there is an uncertainty in the data where you have C, AI, and BI, if you have uncertainty in data, then it will be classified as a robust linear program. And like we can simplify this further in the sense that let us say we want certainty in this AI and BI. In other words, like they are like fixed. Then assume AI lies in, and also assume that AI lies in given ellipsoids, like something like this. Okay, so this is the form of the ellipsoid that we have seen here. Then we get some other variant here. And AIs are assumed to be lying in some ellipsoids. Okay, so there is a constraint on AI itself. Okay, so then we will have a form like this where AIs are coming from the ellipsoids, and then I equals to 1 to m. So we are giving a specific form furthermore to this because they do appear in some applications. Okay, so I won't say much right now. Like you may ask like why I'm taking only ellipsoids and so on, but yeah, okay, I will say that this is one of the form of optimization problem that appears in practice. Okay, so overall in this slide, what I want to say is like there could be uncertainty in the data itself in your model, and that you may have to encounter. Now, just stating this is very easy right now. You can say, what do you want to say, right? And certainly, the crux here is to understand how to solve with those things, right? So modeling is not a big deal right now. Modeling we did, but given that there is uncertainty, how are we going to approach this? Okay. So that is where like we have to see solver. Okay, so we have to focus on solver of this. For the moment, we have to just leave it like that. Okay, so there is something called robust linear programming, and it is defined like this, where the objective is like linear, and then you have a linear inequality constraint with this coefficient C, A, and B to be uncertain. Okay, noisy. Okay. Okay, so I will leave it up to here. The main thing is to discuss how to solve actually, right? So that's something we postponed it for the moment. Okay, and then there is something called semi-definite programming. And so again, as I said, these are the templates, and you have to like remember this short form also you should remember, okay, in future. So often they write just STP. I mean, these things are so like well known that they will just write STP. They will never write semi-definite also, okay, in the paper. So they have exactly this form, okay. So exactly this form. So this is like by I'm saying exactly this form like but sometimes you may have minor changes like this. But as I said, I can always drop this. Okay, this doesn't really affect my optimal value. Okay, I mean you may have liberty to have D also. It doesn't matter, but they are the same thing. Okay, so and then the constraint are of this form. Okay, so this is like a slightly different type of a constraint here. Okay, this is like I have a matrices, and these are symmetric matrices, and I have x1 f1 and then x2 f2. It's like some kind of a linear combination of the matrices itself. Okay, and that is like less than equal to 0. So there is a special structure of the inequality constraint, and then there is a equality constraint here. So it should be exactly in this form. Okay, it should, where G should be, okay, where is G here? There's no G here, right? Yeah, there's no G here. So only F. So F1 to Fn should be symmetric, and E is just any general matrix. Okay. So why do I keep writing G? I don't see G anywhere. Yeah, I hope I have not missed anything here. So if the matrices F1 to Fn are diagonal, so if it so happens that these matrices are diagonal, then you will see that this will boil down to just a set of n linear inequalities, right? Because this will be like x1 and then something diagonal, right? So let us say f1, f2. Okay, so this is like the first, and then x2, and then f1. So this is for the second f, and then the second component. So if they happen to be diagonal, then they will turn out to be just some linear inequality. X2 f1 2 is less than equal to 0, and then x1 f2 1 plus x2 f2 2 is less than equal to 0. So they boil down to just a set of linear. So these are just linear inequality. So that's what it's saying. So if then SDP becomes LP. Okay, so SDP is just a slight extension of LP. Okay, okay. So these were the popular templates of the optimization problem. I won't say these are the only ones, but as we encounter problems in the coming classes, I will define more different variants of these. Okay,
Sir,
so yeah, yeah.
sir, in the constraint there is a plus G in the book. So x1 f x xify sigma xify plus G less than equal to 0.
Yeah, so here I'm missing this G, right?
Yes, sir.
Yeah, so there is some additional G that is missing, right? Okay, so that's why there is a G here. Okay, so it's to make this more general. I can also have some constant metrics applied here. Okay, so that I can take into account the G terms as well. Okay, so I was missing this G term. Okay. Yeah, so we will stop here, and then we will discuss a very important topic, perhaps the most important topic, I would say, in the theory of optimization, and that's called duality. So if you have watched the movie Transformers and you see how it can transform from a robotic human to something like a car or something, right? So in the movie, if you recall, then and the duality, the problem behind duality is the same. It's like can I transform from one form to another form? Okay, so in other words, can I transform from the primal problem to some other dual problem? And some of the hint I gave you, some intuitive ideas I gave you when I was discussing the conjugate functions, and we will see application of conjugate functions in duality. So conjugate functions, we saw what we saw about conjugate functions is like given a given a function, we can approximate the function either we approximate the function on the point values that the function is taking, or we can approximate the function by the slopes, right? So we can take the slopes of the function, right? And in other words, very loosely speaking, I can go from x domain of the function to the slope domain. Okay, so so some intuitive idea I gave you when I was discussing the conjugate, and and that's when we say that we have gone from the given primal problem to some other space where one thing we observed is that the conjugate of a function was convex, regardless of my original problem was convex or not. Okay, so that was a good thing that we saw. So it was always convex. And what we know so far from the optimization is that convex functions are nice in the sense that local minima is the global minima. So there is no such a problem in the sense that I will get stuck at local minima. I will never be able to go to global minima using gradient methods and so on, because gradient becomes flat. So I don't know where to go after that. So, so one of the primary thing in optimization theory is if at all it's possible to transform your problem into a convex optimization problem, then do that. If it is feasible, if it makes sense, okay, then do that. Okay, and then you have very nice solvers for that will guarantee convergence and so on. Okay, and then you go back to your original problem. So duality conjugate functions we have seen is a tool to transform my given function to a dual function. And dual function is guaranteed to be convex. Of course, one can ask what happens to the equality, inequality constraint, and so on, because convex function is not just about objective function being transformed to convex. It's also about the domain being a convex set, the feasible set. The constraint functions must be convex functions. Equality constraint functions must be convex functions. So there is a lot actually. And all these ideas will be stitched together, and you will see that we will arrive at a very powerful idea in optimization theory, and it has applications in across data sciences and everywhere basically. Okay, wherever you have like constraint problems. Okay, so now digging back a little bit into the history, duality history has two main guys. The first guy we have already seen how to find conjugate functions. Okay, so this is something we have already seen in the class. And so conjugate functions is due to Fensel. Okay, and what we are going to discuss next is the Lagrange multiplier. Okay, and that's due to Lagrange, obviously. And both are French. No surprise. Most of the high-end maths were done by French. Most of the modern maths, yeah. So without, yeah, so let us go straight into the problem. Okay, so duality is, as I said, is helpful for constraint problems. Okay, so constraint optimization problems. So this is one such problem that I'm showing you here, where I have an objective function which is fxy is equal to 8 x square minus 2y, and then I'm giving some constraint hxy is x square plus y square. So if I plot, let us say, the constraint, then this will be the circle here in the blue, and that's x square plus y square equal to one constraint. Fxy, it turns out, unfortunately, it's a 3D, right? So it's a surface. If I have to plot this, then it will be a surface plot. Okay, so it will be like a plot in the xy plane, but then I have to put the values above the xy plane, indicating the value at x square minus 2y. Okay, and we cannot do that in general because we are usually using 2D plane to understand things. So So the tool that will be useful. Okay, so now this is the time we will use up the tools that we have invested in and so much, right? So one of the tools we have invested into is level curves, right? So we had an understanding of the level curves. We also did the assignments and so on. So now is the time to invoke those things, tools, to plot instead the level curves, right? So level curves can be plotted in 2D. If it is a 3D function, then level curves can be plotted in 2D. Obviously, if the 4D, then again level curves will be like look like a 3D. So we don't have any hope there. So as far as 3D problems are concerned, level curves can be plotted on a 2D, and these are the level curves as you can see. And if you recall, the level curves were obtained by equating equating the function values to some constants, right? And if you vary these constants, you get different curves, right? So these are the level curves you can see. Okay, so if I put this constant equals to 0, then this is the level curve I will get. Okay, so at 0 0 it indeed satisfies 0. And if I have a c to be -1, okay, so c to be like a -1. So at 0 0, like it should be yeah. So is this fxy is -1? Is this curve right? Yeah. Yeah, is this plot correct? I wonder. Okay, so so at x square minus 2y equals to -1, right? So at 0 0, so at 0 0 the function value. Yeah, so I think we have to check whether this is the correct plot of this.
Sir, it is a correct plot only, right?
It is a correct plot, right?
We can check at x equal to 0
Yeah.
and y equal to 0.5.
Yeah, actually we have to, since it claims that it's passing through this, so we have to check that this satisfies this. And okay, so and yeah, let's see. So at 0 and half, right? So 0 it's 0 minus 2 times and then half. Yeah, it's actually correct. Okay, I'm sorry. So it's -1 equals to -1. So these are correct plots. Okay, so we level curves, if you recall, then for different values of c, we get these different curves. Okay, and yeah, so far what we see is this figure, and we see some level curve has actually just touched this, right? So just touch this x square plus y square equal to 1 graph. Okay, we wonder what was the significance of that, right? Like geometrically, we are wondering what is the significance of that. But let us see what is more. Okay, so what other observations we have? I mean, this guy is a fixed guy. It's a circle of radius equals to 1. We see that some of the level curves are intersecting with this guy. Okay, okay. Look, our problem is to minimize, right? Minimize this function subject to this. So one thing that is very clear is that whatever xy we are going to find out, it has to satisfy this equality constraint. So it must be something on the circle itself. We are not allowed to choose any other points outside that, because that's the constraint. That's the meaning of constraint. So we have to like move around this circle. We have to move around this circle and find out for which values of points on the circle the function value is minimized, right? So that's the problem we have in hand. Now, level curves, if we see from the values it's taking, and we clearly see that if we are going in this direction, right? In this case, the minimum value of fx, I mean not minimum value, but the value of fx is 0, for which the level curve is drawn. And this is the value of fx y, which is -1, which is further minimum. Okay, more minimum. This red one is even more minimum. Okay, so -3 is going more minimum, and so we know that like more and more we are going this way. The function value is like is decreasing, okay, and which is what we want. But the problem is that in this region, the circle is not there. So, so although the function value is minimum in this, we are not allowed to choose those. Okay, so we have to restrict our attention to only the circle part, right? Now the question is like where I should move, right? Where I should move so that I remain on the circle and I minimize the function value, right? And one thing I'm guaranteed is that these values are all the same, right? So if I'm saying that fxy is -1, then it means that on this any point pair of points I choose, they all give me -1, which is like the constant value, right? Okay, so this is one observation. So like any point on these level curves, they are the fixed value and they are indicated by these values, right? Now, it's a simple question now for you to answer. How will you move around this circle so that you hit the minimum? Okay, how will you move around the circle so that you hit the minimum of this function, right? As I said, minimum is going this direction, right? But this direction you are not allowed to go because those are not on the circle. You have to stay in the circle. And how will you move around? Okay, which point you will choose such that the function value is the minimum and you are on the circle. Okay, so this is now more like a combinatorial problem, right? So what logical problem, right? So what do you do in this case, right? There are indeed level curves that gives me lesser value and they do intersect at some point on the circle, right? Like I mean lesser value in the sense like if I compare this guy and this guy, right? So if I see this level curve, then this level curve value is 0, right? So I'm on the circle, I'm moving like a stranger, I'm on the circle, I hit here, I said, oh wow, here my function value, like my level curve is matching, like I'm intersecting with the level curve. In other words, this xy point is on the circle as well as satisfying the function, right? So but is this the smallest possible value I'm getting? No, I'm getting like 0 here. Then I move and explore further. And then I find some other level curve. And then I check, okay, is this the smallest possible value I'm getting? I said, okay, no, I'm getting -1, right? So I'm saying, okay, so far this is the -1 is the smallest, right? But we also know that there are like infinitely many, like I have not drawn these intermediate level curves also, right? And there will be one more intermediate, not just one more, infinitely many, right? So there could be so many level curves, right? Now the question is like how far I will move and I will keep hitting the smaller value, right? So as I was going in this direction, I know that I hit 0 value, I hit like continuously I'm decreasing, right? So 0 and then less than 0, right? So it's just like something which is very less than 0. So -0, 0, 0, 0 something and then so on. And then I hit -1. So it's like I am at 0 and then I'm hitting. So least value I saw so far is 0 and then something else, something else, something else. And then I hit -1. So I'm getting a sense of how I have to move, right? So I will keep moving. And what I find is like, if I reach a point where the level curve just touches, that happens to be the point that gives me the least value. Okay, that gives me the least value because like if I like go just immediately beyond that, I start hitting level curves which are again giving me higher value. Remember this guy, if we focus on this -1, right? So this red one is -2, right? So I reached here, I got the -2 value. Now moment you go here, you start hitting level curves that are taking higher values now. For example, if you move here and you reach here, then you hit a level curve which was the level curve of -1, right? Which is higher value. That's I don't want, right? So intuitively now it is very clear that it has to be a point which just touches the level curve. Okay, so the point of minima is a point where you will just touch a level curve Okay, you will just touch a level curve. Okay, so that's the intuition behind this. And like mathematically, what will this boil down to, right? So mathematically, this will boil down to, if I like now remove this point. So what I will boil down to is, how do I characterize this point, right? So I was coming here and then I hit here, and then it's the point where the level curve just touches, right? So mathematically, what does this mean, right? Um, Mathematically, what it means is like when two curves are touching, right? So two curves are touching like this, let us say, then it means that at that point the tangent is like parallel for both, right? Okay, so there is a point of touch and where the tangent is parallel. So if I draw a tangent to the red one and if I draw a tangent to the blue one, both will be in the same direction, right? They are like parallel. And like depending on which direction is increase or decrease, okay, it will depend on which direction increase or decrease. The gradient will point either outward or like this way, right? So the only question is, so I know that the tangent is parallel to the level curve, right? So I know that, so this is something we have proved before. So this is the tangent now parallel to the level curve, right? So the increasing direction gradient points in the direction of increase, which is this. Okay, so the gradient of f here. Okay, and in the gradient descent, since we are interested in minima, we go in the direction of decrease, which is like this way, right? Minus grad f. Okay, so these are the things we know. So now, okay, so this is the gradient, and then we have a gradient of these equality constraint also, right? So we also have a gradient of h. Okay, so we have a gradient of h as well. So we have a grad h, and which is also perpendicular, obviously, because again it's a gradient. So this is like gradient of h, which is also perpendicular to this tangent. In other words, grad h and grad f are in same direction. Same in the sense like they may be anti-parallel, parallel. Okay, it doesn't matter depending on where the grade is increasing or decreasing. And grad h. So grad h and this and grad f are parallel. Okay, are parallel. Okay, by parallel I mean there can be also anti-parallel. Okay. In other words, one is a linear combination of the other, right? So grad h is some lambda times grad f. Okay. Now this is the mathematical characterization of this. Okay, so it's like I have figured out what this really means. So solving this problem now boils down to satisfying this constraint along with obviously the equality constraint plus and okay, so sometimes you so plus the equality constraint y square equal to 1. So my original problem now, if you see, has been reduced to set of these conditions. Okay, so if it so happens that I mean these are like set of some systems to solve. Okay, this is quite different from the optimization problem, right? Originally, optimization problem never looked like solving a system of nonlinear equation, but now we have reduced our problem of solving optimization problem to solving a system of nonlinear systems, possibly nonlinear system, because this grad f can still remain nonlinear, and this is already a nonlinear. So what we may ask for now after this is some good nonlinear solver. Okay, so that's like another thing to look for. But from here, what we understand is like a optimization problem with equality constraint, okay, can be reduced to system of possibly nonlinear equations, and we may try to solve that. Okay. You may wonder how many equations are there, how many variables are there. We will look into this a bit later. Like you may say that now you have lambda as well, x and y, and is it like only one? But technically there may not be one. There may be three equations here. Okay, because these are like vectors, right? So yeah, so we will be able to solve this. I postponed this for the moment, but what we observed so far is that we have this two set of nonlinear equations to satisfy. Okay, and this is kind of a vector equation, so it's like combination of equations, and this is one equation here. So together with this, we should be able to solve for that, and that is exactly the criteria where this satisfies, and that is exactly the point where minima is achieved. Okay, so that's what we are looking for in the optimization problem anyway. So it's solving this is exactly the same as solving the optimization problem. So this is what I have written, what I have described so far. This is what I have just summarized. So the stepwise, what you do is that you draw level curves and the constraint set. This is what we did. Function takes the minimum where it just touches the constraint, and that is what I have explained. At the touch point, the normal to the constraint curve and the level curve are parallel. So that's also I have told you now. Okay, because the tangent will be flat and the gradients are perpendicular to the tangent drawn on the level curve. That's proof we have done before. So it applies to the both the curves, and then in that case they will be dependent on the other. So when two vectors are parallel, then one is a scalar multiple of the other, and that's what we have done. And just to note down here, lambda is called the Lagrange multiplier because Lagrange was the one who discovered this idea. Okay. Okay, so this is the starting point of the duality theory, where you have already seen one method where you can eliminate equality constraints by using introducing a Lagrange multiplier. I can so I can like give another intuition behind this duality. Let us see how. So this is now a very abstract form. Okay, so the previous one was a example, motivating example, but I can give an argument in a very general sense. Let us see how. So we are given an optimization problem to solve. So in this case, it's minimize fxy and there is an equality constraint. We will see inequality constraint later on. Okay, so the constraint, as we have seen, hxy defines a curve. Okay, and if we differentiate it with respect to x, so if we differentiate this with respect to x, right? So d by dx of hxy. So remember, in general, the d by dx of a function like this, g1x, g2x, gkx. Okay, I have described this before. What was this? So there is a chain rule, but there is also a like multiple of these, right? So what was this? This was del f by del g1 dg1 by dx plus del f by del g2. These are the things we will also see when we discuss neural networks again, right? So dg2x and so on. Okay, if we apply this here, but this x and this x are same, right? So in this case, we will have del h by del x and dx by dx. Dx by dx will cancel. Okay, so that will be just 1 plus del h by del y and dy by dx, because we are assuming y may be dependent on x. Okay, so dy by dx. Okay, and yeah, and then if we do this, and then right hand side will be 0 anyway. And we know that the gradient of the curve is denoted by this. So we know that the gradient, so I could have put 1 here, and we know that the gradient is perpendicular to the tangent, right? So from here I can extract the tangent because I know that the gradient is this guy. So I see this as a dot product of del h by del x, del h by del y, and then I extract the other part, which should be a vector along the tangent, because that's what we know, right? So dy by dx. So this is equivalent to this. So this is the gradient, and I know that gradient, if it is perpendicular to a vector, that must be the tangent vector. So this must be the tangent, vector. Okay, so we also know what is the tangent vector. So tangent vector is this, like I just described. So in other words, t dot grad h is 0. The tangent must be normal to the gradient. I mean, this is the proof I think we already discussed. Okay, I think I'm recalling this again. Okay, but let us see what happens in the general case, right? So I have a constraint, and my problem tells me that I must be on the constraint all the time. So the first step itself is that I never leave this. Okay, this is the restricted path I have to follow. So this is the constraint path, and it is some curve. Okay, so somewhere I'm here. Okay, and then if I draw a tangent, then it's like the instantaneous direction of my movement, right? Instantaneously in which direction I'm moving, like very small enough, right? So I'm moving in this direction, right? I draw another tangent, then it tells me instantaneously where I'm moving in the next instant, right? And then I always know that the gradient is perpendicular to the instantaneous movement, right? So these are like just the calculus part. So to stay on the curve, the motion must be along the tangent, right? So my motion must be along the instantaneous tangent, right? Of course, I will not move so far that I move here and then I'm out, right? That's not the case. It's just saying instantaneously along the tangent. So it should be just along, right? So that's fine, okay. And then now we also bring in the gradient of our objective function in picture, okay. Now the question is a very basic question is, remember in the previous example also we saw, we had a circle and we had to move around the circle. And then we were moving around the circle and we were asking for wherever the function is decreasing. And then we were keeping track of the level curves, and level curves are like a good intuitive things to see in the 2D. And then with that we found where actually we should hit the minima, okay. So so there is there is something more here, like the something more which is here is like, what is the rule to move, right? So previously, like I was moving in an ad hoc way, ad hoc in the sense like I did not specify any rule to you, right? Like what is the more precise tool or some measure I have in hand that tells me, like if I'm here, like given, let us say you are in a very big dimensional space and so on, right? Like you cannot really go here and there and check, okay, here the level curve is minus, and then I have to go here and here, and imagine that this equality constant itself is in a very big dimensional space, right? How will you do hit and trial like this, right? How long you will do hit and trial like this, and then you will eventually hit the minima, right? So there must be some guidance, some way that tells you that, okay, maybe you should follow that way and you are guaranteed that your function is going to decrease, right? So that way you should go and then your function is going to decrease. Now, I know, so what are the tools I have, right? The most important tool I have is the gradient of a function, right? So gradient points in the direction of increase. So this is the gradient that points in the direction of increase. So I know that I have to go in the direction of decrease. So I will follow minus grad f direction, right? Now, can you not use this as a rule to, let us say, if I give you this point here, can you not use this rule to identify where you should go now, like whether you should go this way or whether you should go this way? You are constrained to stay in the circle, that is guaranteed. But is there a tool in terms of grad that will tell you which is a proper direction to move, right? Which is a proper direction to move, right? So how do you identify, right? Or it could also be the case that that both way you may be decreasing, not in this example, okay? In this example, if you go, you are increasing surely, but it may be the case that both ways decreasing, but you have to make a choice which is the most decreasing case, right? So it has to do with something with the tangent, something with the gradient, right? It has to do something with the gradient. In other words, the directions that you are moving, let us say this is the direction you are moving. If the component of your direction, okay, if the direction you are moving is more aligned, okay, more aligned with the negative of the gradient, right? In this case, it's the negative of the gradient f. Okay, so let us say this direction, and your direction of movement, other direction of your movement is this, and then the gradient is, let us say, this. So which one is the good direction to go, right? This is more aligned to your grad f. Okay, and this is not so more aligned. In fact, this will be the worst case actually. Okay, you will neither see decrease or increase because it is like exactly like perpendicular. Okay, I will come back to this case later. But what I'm trying to say is, like, more aligned you are towards your this, it means that you have more component of your travel along this. It means that you are going to minimize more along this direction, right? And lesser along this direction, although both may be decreasing. So to be more appropriate, let us do this. So this is more, and this is more aligned to this, and this is less aligned to this. I'm not talking about the length that you, because length will also determine, right? Length will also determine, because if I took only this step and gradient remains this, although I took a not so closely aligned, let us say this aligned, but I took a lot more. So eventual decrease will be more here because I moved a lot more. Although the decrease was less in this, I moved a lot more. So eventually I decreased. Okay, but assuming that your movement is unit, okay, unit movement in each direction. So it will depend on how closely you are aligned to the grad f. Okay. Okay, now with this intuition, let us go back to the figure. Okay, so so we have this tool to tell us like how how I should move actually, right? Rather than saying just randomly and then checking the level curve value, right? So to be able to increase or decrease, okay, so to be able to increase or decrease, motion along the constraint must have a component along the gradient of f. Okay, so to want to decrease, then you have to have, I did not specify specifically whether you should move along grad f or minus grad f. I didn't say that. To decrease, you should go along more specifically, you should go around minus grad, and to increase, you should go more specifically towards grad f. Here we are making a general statement to increase or decrease. Okay, to increase or decrease, at least you should make sure that you are along grad f or minus grad f. Okay, okay, but you should be along grad f. Okay, whether you take positive value, negative value, doesn't matter. It will increase or decrease, but you must have some component. The point where you will stop is exactly the point where you have no component, right? Where you have no component of your tangent. So if we go back to the circle example, the point where it's touched, if you see, okay, this became exactly orthogonal to this. This means that now grad h, not grad h, I mean the tangent, okay? So this tangent at this point, the tangent has now no component at all. Okay, no component, because if I write the tangent as a vector, let us say tx and like ty, okay, and let us say this is my axis, and now I arrived at this touch point. Now the tangent has only x component left, okay, and y component is 0, okay, and my gradient was in the y component, right? So this was my gradient, okay, and gradient had only y component left, okay, according to this figure, okay. So let us say some y component was there, and tangent only has some x component here, okay. So some x, let us say, and 0, okay. So they don't have any component matching. In other words, their dot product is 0. So all these are same thing, right? So the point where the tangent has no component left, in other words, it becomes perpendicular, right? No component left along the gradient. That is the point where instantaneous increase or decrease, instantaneous, okay, instantaneous increase or decrease will not lead me to anything interesting. It will not lead me to any maxima or minima. Instantaneous, okay. So if we go back, so must have, so to keep increasing or decreasing, so to keep increasing decreasing, I must have some component all the time, okay, to keep increasing or decreasing. And in other words, the criteria that we have is this, okay. In other words, the dot product of them must not be 0. In other words, like my movement direction and then the gradient must not vanish, okay. As long as it does not vanish, I will either increase or decrease, okay, depending on how I am moving. That's another thing, okay. So so in other words, at extremum, so we are like making a general statement here. We are not necessarily talking about maxima or minima. Let us say anyone, right? So an instantaneous motion should not yield at extremum, right? At extremum, the instantaneous motion should not yield a component of motion along grad f. That's what we discussed, okay? So once we have reached the extremum, it could be maxima or minima. And at that point, at extremum, my tangent should not, because otherwise, on the contrary, if it, then naturally by movement I will increase or decrease, and I will violate the case that I was at extremum, right? So it should not have any component along grad f. Okay. So at extremum we must have this, right? So that's the criteria we got. Again, like some condition we got, mathematical condition we got, that at extremum this is the condition that has to be satisfied now. Okay. So T is orthogonal to grad h always, and now T is orthogonal to grad f. Okay. So again, like this is all this is same thing as saying like grad h. This is just another view of the example. Okay. So I'm not saying anything more. We are arriving at the same condition, but just in a more abstract sense here now. So grad h must be parallel or anti-parallel, okay, to grad f at the extrema. And if that is the case, then it means that the grad f must be some lambda times grad h. Well, instead of lambda, I can also take minus lambda just to keep it clean. Like I don't want to see negative here. So I can take instead of some minus lambda. And then the criteria will become grad f plus lambda grad h is equal to 0. Okay. So that's the condition seen in an abstract way. So the way things go now, it's very clear. So I will just go through this again in a very quick way. Now this is abstract setting. Okay, h is some constraint, which is the blue curve here. I am moving. I started from x1 y1. So superimpose the curve x and then this, and then CIs are this, and then tangent of the level curve is always orthogonal. Imagine a point moving along the curve hxy, started from x1 y1. You keep moving along this, and the moment it touches the level curve, that's when you stop. Okay, and resulting in the decrease of the value and so on. Okay. So yeah, so the component of the motion along minus grad f gets smaller. So as you are moving along, the component of the motion along this gets smaller. When the motion reaches this, the motion is orthogonal to the grad fx. After this, if it's continuous along this, the motion has a component along grad f, and the function value will decrease. Okay, so it's like there is a further addition that is going on here. Like let us say in the context of the minima, if this is given to be the yeah, so if this is given to be, so at this point, right, at each point I'm seeing, right, so grad f, and this is the minus grad f. So since I'm interested in the decrease, okay, so this is minus grad fx. So this way I should move. Okay, if I was interested in increase, then I should have move in this way. Okay, so all this is just saying this way, the same thing that I said. Okay, and then at x star y star, the function achieves a local minimum, which is c star, and at this two gradients are opposite. Okay. So after all this, what we found is like to minimize the function with some constraint, equality constraint, it reduces to solving a set of nonlinear. It reduces to solving a set of nonlinear equations, right? So the system of above equations can be described by using so-called Lagrangian. So this is the parameter Lagrangian, and this condition. I'm sorry. Okay, Lagrangian will be defined separately. Actually, if you see this constraint, what you see here is like there is a f involved, there is a h involved, and it's like I have summed them, and then I've taken a gradient, right? So it's like I have taken a gradient of this, right? So I could have defined a function like this. Okay, so given a problem like this, objective and equality constraint, remember that there should be 0 here. Okay, because if there is constant here, that is not h. H will be h minus, you have to put back the c here and then involve in h. Okay, so the Lagrangian condition that we have here can be defined by first writing a Lagrangian, so-called Lagrangian, which is sum of f and h, and then lambda also. And then if I take a gradient, because gradient is a linear function, so the gradient is grad of f plus lambda times grad of h, and which is exactly the the constraint that we wanted. So a proper way to do this is first define a Lagrangian, which is sum of the objective and then the equality constraint function times lambda, and then we do grad L equal to 0, and that gives us this this additional condition. So that's what we did. We defined a function L, which is called the Lagrangian, and then we added, and then if we do the grad H, okay. So yeah, okay. What did I do here? So here I have yeah. So this was like a grad L, and additionally I have put H here. But why should I use this notation? And this will be a bit, because H is being used here already. Should be something else, I think. Let me use some other variable, okay? Okay, let us say G here, okay? Okay, so I have formed this, which could be seen as this. Like, we have written this compactly, right? If you see here, like, all this can be like written compactly, right? So as a, this is like grad F plus lambda grad H and H as a vector, and this equal to 0. That's what we have, right? So I can club in both these conditions as a vector and equate it to 0. So that's what is being done here. Okay, and yeah, so we can have this, and setting grad L equal to 0 obviously gives the nonlinear equation that we have, right? So grad L is this, okay? Okay, so so these are the set of conditions we have been talking about so far. Okay, these are just way to like write things. You first write Lagrangian and so on, but eventually what matters is this set of nonlinear equations that we are supposed to solve. Now let us see some example so that you can actually solve problems in practice. So let us see a function like this. Objective function is xy. Okay, so and then the constraint is subject to hxy is this. Okay, so it's like an ellipse constraint, x squared by 8 plus y squared by 2 equals to 1. So what are the steps we have? First step is to define the Lagrangian, right? So Lagrangian is the function plus lambda times the equality constraint. And remember that one has to be brought here. It has to be of the form hxy equal to 0, right? Okay, so we have the Lagrangian, which is defined to be fxy plus lambda times hxy. Okay, so this is the Lagrangian, and if we take the gradient of the Lagrangian, okay, and if we take the gradient of the Lagrangian, and then we also put the equality constraint here, okay. Okay, I see. So actually the way to do this is like in the Lagrangian, if you see, if you take the derivative with respect to lambda, it produces the equality constraint. Okay, so this is a nice, neat way to actually get the equality constraint as well. Remember, so this guy is del L by del lambda. Okay, so this guy is del L by del y, and this guy is del L by del x. Okay, so if I see here, so this is L. Okay, so the whole thing is the Lagrangian. So this was by del L by del x. This was by del L by del y, and this guy was del L by del lambda. If you do partial derivative with lambda, you are left with h. Okay, so Lagrangian actually compactly satisfies everything that I need, right? So Lagrangian equal to 0 is exactly the set of nonlinear equations that I'm supposed to solve to find a solution to this optimization problem. So now this means what? This means these. So entry wise they are equal to 0. So this is the set of nonlinear equations to solve, right? So now if you maybe substitute here and there and cancel things and so on, sometimes you may be able to solve this in a straightforward way. Okay, so let us see if we could solve this problem. So now it's more about solving nonlinear equations. So let us say this system, and can we solve this? Eliminate x from the first and second equation. Okay, so if I eliminate x, so I solve for x here. So x is like minus lambda y, and then I put x here, I believe, and that will give me this. Okay, and okay, so what should we conclude from here, right? So can y be 0? Okay, assume y is 0. If y is 0, then x is 0, and if y is 0 and x is 0, will it satisfy this? No. Okay, so those are like are thrown away. Y 0 cannot happen, so the other must happen. Okay, so y cannot be 0 because then x will be 0 and it will violate, and it violates equality constraint. Okay, so that's not gone out of the window. So and then here so the only possibility is that lambda square is 4, then it cancels out. In other words, lambda is plus minus 2. So yeah, lambda is plus minus 2, both are valid. And then from the, if lambda is plus minus 2, then from where we can solve, right? So from the second equation. Yeah, so from the second equation, it gives me x is minus plus 2 y. Okay, and so there seems to be like the 4 extremal points of f subject to this. Okay, so yeah, so x must be equal to plus minus 2y, and if I put this in the third one, right? Yeah, so if I put this in the third one, this will give me various values of y. Okay, and then for those I can solve for all possible x and y. Okay, and if so these are the solutions to this simultaneous set of nonlinear equations. Now if we look this into so far, remember, this Lagrangian doesn't tell us anything about whether we get a maxima or minima. Remember, our theory as such did not tell us whether it's like a maxima or minima. So in this case, like, we have to now identify on our own which of these points are maxima or which of these points are minima. So maximum value is actually achieved at this. Okay, so we just substitute these values in the fxy. Okay, so in our case, the fxy was xy, right? Yeah, so xy, so 2 times 1 is like 2, right? So it's 2. So these are the maximum value we are getting. And this is like minus. Oh, okay, there is a mistake here, right? What is that? Yeah, so I have duplicated the values here, right? So it should be pairwise. So this was fine, and 2 minus 1 and minus 2 1. Okay, so in either case I'm getting minus 2 minus 2. Okay, so this has to be like the minimum value, and these are extrema, so no other point has to be tested anyway. So this is the maximum value I get, and this is the minimum value I get. Okay, okay, so now if we see this in the graph, then remember 2 1 and minus 2 minus 1, right? So this is like 2 1, so this is the point 2 1, and minus 2 1 is this point. Okay, and oh, sorry. Is this correct? Minus 2 minus 1, right? Okay. So minus 2 and minus 1 is this one, right? Yeah. So minus 2 minus 1. So let me remove this. Oh, okay. The point was okay, right? So what we are claiming is like these points are the maxima, which is true because if we plot the hyperbola xy is 2, which is the level curve for this guy, right? So if we plot the graph of the hyperbola, then it looks like this, right? So this is the plot of xy is equal to 2. Okay, so so this is the maxima that I get. And once again, remember, ellipse was our constraint. So constraint, and we moved around and we found like where it just touches, right? And those touch points were these 4 points in this case. And then like touch points could be maxima or minima, right? So but out of this 4, we found that these are diagonally opposite ones, like somewhere here and somewhere here are the maxima. And then similarly, we had the xy equal to -2 hyperbola, and then there we had the minimum value. Okay, so this is an example of, so summarize, to reach to your objective. The point here is that the way you are moving around, your tangent must have like some component along the increase. So if I'm walking towards, let us say, some Mount Everest, then in general my goal is to move in a way that I have some component along the increase. So this valley is increasing in this direction. So my component, my direction of increase is also in this. So this is the grad that is pointing me. So our eyes are kind of computing all this implicitly for us. We see the gradient through our eyes, and then our path is restricted because other paths could be dangerous. So we don't want to take those paths, and then we move, we remain on the constraint, which is the red one, and then we keep moving until we reach the goal. Okay. So yeah, so as humans, we have a much wider view than the local. So you can say that the gradient methods are like maybe even a little bit more dumb than the human beings, in the sense that our eyes can somewhat see the gradient more far away. Like I see that there is a higher steep here, and there is a steep, but it's like not that much. And in fact, momentarily there may be a decrease as well. So there may be a decrease, but I have a global view, right? So I can see that some point further ahead I can increase. But if we use the gradient methods, then it doesn't tell us anything ahead, right? It only tells us local decrease or increase. And if by using that information we stop here, then we did not really proceed forward, right? So, okay, so if we try to formalize things, right? So we can actually have inequality constraints as well. In general, the problem can have inequality constraint, and Lagrangian can be defined also for inequality constraint. Now the question is like, how will you extend your intuition? So far you have seen that there was an equality constraint, right? And then you were moving around this equality constraint, which is usually a curve, and you move such that you hit the point, touch point of the level curve, and that's where you stop, right? So now how does your intuition extend to the cases like this? So these are intersections of, so I could have functions like this, and then I have some equality constraints passing via this. So this is let us say inequality constraints. So intersection of inequality constraint may give us some bounded region because of these inequalities. It may be unbounded also. So it could be a region like this, and it's just less than equal to 0 will denote this region. And then I have some equality constraint that passes through like this. Okay. And then in all this, I have some level curves of function. So some level curves is going on. Let us say some level curves are going on, right? Like this. Now the question is, what do you do? Right? What do you do in this case? Like the intuition, one of the intuition that tells you is like, I mean, if this is inequality constraint, but overall, if I intersect with this, eventually these guys are going to be like, if this is going to be a curve, overall these guys are, because this has to intersect anyway. So the set of points x for which this satisfied has to satisfy this, or the set of points that has to satisfy inequality has to satisfy this. So eventually it boils down to sticking to the equality constraint. But only thing is like, some points of this may no longer be valid anymore because they were not satisfying the equality constraint. So it's like it's just an extension of what we did, but it's just that some group of points may no longer be satisfying the inequality constraint. So those we are going to discard, but we got to remain on this constraint set. Okay. So the intuition will somewhat follow. I may not be doing this more, but the intuition will somewhat follow again, and then the idea that it has to like touch some level curve. Okay, so I think I took this as the equality constraint curve, and let us say the level curves are like this, right? So then like we will keep moving and so on, and then we at some point like we believe that it will touch, and then the gradient and all this will be perpendicular and so on. Okay, so intuition will extend even if there is an inequality constraint. Okay, it's just that now some points are getting removed from my equality constraint curve. Okay, not all points are going to be removed, otherwise there will be no solution because none of them satisfied the equality constraint. Right, so yeah, so some point may be removed, may not be removed. There are many cases, right? Okay, so so in general, what we will do now is that the Lagrangian in the general case will involve all this. Okay, so it will involve the inequality constraint. Okay, and it will involve the equality constraint, and then I will have a parameter with respect to the inequality constraint, and I will have a parameter with respect to the equality constraint. Okay, and a more general Lagrangian in the case of inequality as well as equality constraint will look like this. Okay, so and then here lambda I and nu I are called Lagrange multipliers. Okay, and lambda and nu are called the dual variables or Lagrange multiplier variables. The reason why they are called dual variable, remember I started with duality, duality, and I said that I can go from primal to dual. So by introducing these Lagrangian, I see that some new variables came in picture, and these new variables that came in picture are lambda I and nu I, right? So far this was the variables, and this is additionally there. But the idea is like to go to the dual, we will somehow eliminate the x. So eliminate x and keep it a problem in nu, and then we will be solving just a problem in nu. So that this will be an optimization problem in nu, and that's when we say that we have gone from primal to dual problem. So dual problem. Okay, so these are the sequence of steps that we are planning to see. Okay, so I think we may have to stop for today, and we will look into this. Okay, in the next class. Okay, and we will try to solve some problem, not some, but quite a few problem. Even SVM, the support vector machines that we will see, makes use of these a lot. So we will solve those problems as an example. Okay, so I think I will stop here, and if you have questions, then you can ask your doubts now. Okay, so I will be here for a few minutes. Okay, then I will stop. Okay, thanks, and have a nice day. Bye.
Hello, sir.
Yes.
Sir, will it be possible to extend the deadline for assignment 3